Hello and welcome back to PC Retro Programmer. In this video I'm going to go through an example of a couple of bits of code that I have to explain how we can get a rough idea how long assembly language code takes to run. Now we'll mainly be talking about the 8088 CPU today, but we're also going to do some timings on the 8086 and the 286. And the bits of code that I want to discuss are on the left here. So both of them are for doing the same thing. They're for bank switching in CGA graphics. So basically the CGA card has 16 kilobytes of memory, but in the graphics mode, all of the even lines are in the first half and all of the odd lines are in the second half. So if you want to draw a pixel or something on the screen, you need to figure out, based on the y-coordinate, whether you have an odd or an even line, so whether that y-coordinate is odd or even. And you need to add 8192, which is half of the video memory, to your offset if you have an odd line, so that you get into the second half of memory. And so I use this piece of code in my lead-in, for example, in line drawing and circle drawing code, to set everything up so that the offset has this extra 8192 if it's an odd coordinate. So the Y coordinate will be in the AX register and the offset will be in the DI register. Now this piece of code here was submitted by a viewer, Jim Leonard, and this is what he uses, which he claims will be slightly faster than mine. And so the question is, how would we roughly estimate these to try and figure out which is likely to be quicker? Of course, to get the definitive answer on that, we're going to have to do some timings, and we'll do that a little bit later in the video. Now, both of these pieces of code start off the same way. Y is in the AX register, and to figure out whether that Y coordinate is odd or even, we use the shift right instruction. Now, obviously, normally you'd use shift right to divide a value by 2, and actually we usually need to do that when we're doing this kind of offset computation, but that's not relevant in this piece of code. What we're actually using here is a side effect of the shift right instruction, and that is that the carry flag ends up being set to whatever the lowest bit of AX is. So whatever register we have here, the bottom bit is obviously going to be shifted out by this shift right, and where it ends up is in the carry flag. So in other words, if this value was odd, the carry flag will be set, and if it's even, the carry flag would not be set. And that's what we use to end up with a different result depending on which case we're in. Now, the two pieces of code differ quite a bit after that, and I've already discussed exactly how this one works in the video on horizontal-ish line drawing, so I won't cover it again here. But this piece of code is actually even a little bit simpler to understand. We use a conditional jump here, jump if no carry, and basically if the carry flag is not set, it's going to jump to even line, so down here, and it will skip this instruction in the middle. Now if the carry flag is set, in other words if AX was odd, then this instruction will actually get run. Alright, so just looking at these two pieces of code, well there's 4 instructions here and just 3 here. I mean this is just a label after all. So maybe this one is faster just based on that. Well, unfortunately that's a little bit too simplistic. But if you have a book or an online resource, and I'll put a link in the description to one of those, then you can actually look up tables of the times in cycles that each of these instructions takes to run. So the execution time, in other words, the number of cycles that the CPU takes to execute each of these instructions. And you could just add those up. And so that might be one way that you might try to get an idea of how long this is going to take to run. But on the 8088, this doesn't work out at all. In fact, this code is going to take much longer to run than those execution times would seem to indicate. So we have to figure out what is actually going wrong here. Why are those execution times so badly out? Now it is true that those times are the number of cycles that the 8086 and the 8088 take to execute these instructions. But there's something else on the 8088 that takes even longer. And so that's what we're going to discuss here. Well, the thing that slows the 8088 down is its memory access speed. So both the 8086 and 8088 are 16 bits internally, but the 8088 is a kind of El Cheapo CPU, which only has an 8-bit external data bus, unlike the 16 bits of the 8086. And so that means that it can only communicate with memory 8 bits at a time, or 1 byte at a time. Data from memory comes to the CPU, or goes from the CPU to memory over the bus. So we need to figure out how long these bus cycles take in order to know how fast our program is going to be. Now you might look at this code and say, yeah, but where are we actually accessing memory here? Why is that relevant? And you're right, this is all done with registers here, so we're not actually accessing memory directly with our program at all. It would be relevant how many bus cycles it was going to take if we were, but we're not. So why is memory access here important? Well, the CPU still has to read these instructions in from main memory so that it can execute them. So it has to load the instructions, the machine code that these get assembled down into the CPU so it can be run. That is actually the bottleneck in the end. It actually takes longer to load instructions from memory than it takes to execute them. Now the good news is that these CPUs can both execute instructions at the same time as loading them into the prefetch queue. Now of course it can't execute instructions that haven't been loaded yet, but basically once an instruction's been prefetched, it can then be executed while another instruction is being prefetched in the background. So they're just independent processes. So basically we need to figure out a way to compute how long it takes to load code in. And there's actually an easy rule of thumb, and that's because each byte of data that goes over the bus takes a bus cycle, and a bus cycle is exactly 4 CPU cycles on the 8088 machines. So basically, if we can figure out how many bytes of machine code we have here, once this is all assembled down, we can just multiply that by 4, and we've got the exact amount of time that the CPU will take to read that in from memory. And that turns out to be the real bottleneck. The actual execution times are not anywhere near as high for most instructions. There are some exceptions. Multiplication and division instructions are very slow. Jumps and calls and interrupts, and there are various other things like shifts by more than 1 bit. But most instructions take longer to read into the CPU than they take to execute. And so whichever ends up being the larger of the 2 times, that's the bottleneck. Now, in order to figure out how long this piece of code is going to take to run, we can look up tables, either online or in a book, to tell us what machine code bytes this is going to assemble down to. And I think this instruction will be 2 bytes. This should be 2 bytes of machine code. This one should be 4 bytes, because there's a 2-byte constant at the end of that one. And this one should be another 2 bytes, I think. So a total of 10 bytes. And 10 bytes means that it's going to take 10 bus cycles to read in, and so that's 40 CPU cycles. So that's a very reasonable estimate of how long this will take. The only thing is that there are some additional overheads which you have to be aware of. So the bus is actually quite frequently tied up dealing with memory refresh. So the dynamic RAM in these machines needs periodic refreshing so that its contents don't fade. And so if you turn that off, well, your program is just going to fade out of memory and the machine will just hang. So you really need that, and that adds some overhead. The other thing is that the CPU could be dealing with interrupts. And for example, if someone presses a key on the keyboard, that usually generates an interrupt, and there are other things as well. And the CPU has to run interrupt handlers that literally interrupts your program to go off and execute them. And so that adds overheads as well. Now you can turn interrupts off, but of course a lot of stuff's going to stop working, so it's not a good idea either. But anyway, I usually add 8% in total, and if we have 40 cycles here plus 8%, I guess that's a little over 43 cycles in total, including the overheads. So this piece of code turned out to be quite easy to analyze, but this one down here is not going to give us such a simple time. Now, first of all, this line will be the same. That was exactly what we had up here, so we already figured out that's 8 cycles for prefetch. But then things start to get a bit weird. So in particular, these conditional jump instructions can actually take longer to execute than they take to prefetch. So we really have to consider the execution times here as well. To make things even more complicated, these conditional jumps have 2 different times. One if the jump is not taken, and one if the jump is taken. So there's really a lot to analyze. So let's go through it step by step. The first thing is, this is a 2-byte instruction. All of these conditional jumps are. They have 1 byte for an opcode to specify what kind of conditional jump it is, jump if no carry in this case. And they have 1 byte for an offset, the number of bytes that it has to jump if the jump is taken. Now of course these jumps can go in either direction, so that's actually a signed value, but it has to fit in a single byte. And so we have 2 bytes in total for the instruction, and that means 8 cycles to prefetch. So that'll be the absolute minimum that this instruction can take in either case. Now let's consider the execution times. So first of all, the manual says that if the jump is not taken, the execution time is just 4 cycles. But if the jump is taken, the execution time is a whopping 16 cycles. So basically the prefetch is the bottleneck if the jump's not taken, but the execution is the bottleneck if the jump is taken. So we have a prefetch of 8 if the jump's not taken, and an execution of 16 if the jump is taken. So we're going to expect as many even lines as odd lines on the screen. So probably we expect this branch to be taken roughly half the time. So what we can do is just take the average of the 2 times. So take the average of 8 and 16 is 12. So we'll take 12 cycles on average for this instruction. Alright, now the only other instruction to look at is this one, and this is actually 4 bytes, and that's because there's a 2-byte constant at the end of this, and the rest of it's 2 bytes. So we have a total of 16 cycles to prefetch this, and that'll be the bottleneck in this case. But we have a slight complication. This instruction's only run if the branch is not taken. So it's only run half the time, in other words, the way this is going to be operating. And so basically we should take an average of 8 cycles for this to account for the fact that it's only run half of the time. So if we add up everything that we have so far, 8 here, an average of 8 here, and an average of 12 here, I make 28 cycles. But that's not all. Unfortunately, there's a little bit more. Think about the case where the branch is taken, and think about what the prefetch queue is doing while it's executing this instruction. Of course, it's just loading the next instruction. It has no idea that the branch is going to be taken. It thinks this is the next instruction to be executed, and so the prefetch queue is merrily prefetching this while this is executing. And that's wasted time. Eventually the CPU will realize, oh, the branch is going to be taken, and so all of that time is wasted. The prefetch queue will have to be emptied, and it'll have to load this instruction instead. So that causes a stall. And I actually don't know exactly how long these stalls are, but I'm just going to guess 2 bus cycles. It's just a guess. could be wrong. So let's say a guess of 8 cycles stall, but there's only a stall if the branch is taken, because that's the only time it's going to waste time prefetching this. And so on average we have to add an extra 4 cycles for our stall. So we were already up to 28, and so that now takes us to 32 cycles. And now we have to add on top of that some overheads, and so we'll just add our 8% overheads, and so I make this 34.5. It's just a guess, and we'll see how close I was a little bit later. So basically 34.5 versus a little bit over 43, let's just say 43.5 to round things out. And so this looks like it's going to be quite a lot faster than this one on the 8088. Of course, on the 8086 and the 286, there's going to be a totally different calculation of the times here. So this is only valid on the 8088. But the only way to really find out whether it's going to take that long or not is to actually time it in practice and see. So that's what we're going to do today. Now let's take a look at the actual code that I wrote to time these 2 snippets. So the first one I called Bankswitch2 Asm, and I just cut and pasted this code over and over again. And I got tired after doing that 100 times, so the body of this loop has the same code 100 times repeated. And it has a loop that's going to run 47,700 times. So in total, the bank switching code is going to run 4.77 million times. Now you might recognize that number because the original IBM PC ran at 4.77 megahertz. So in other words, the CPU does 4.77 million cycles per second. And so what this means when you set the code up this way is that on the IBM PC, or at least on a 8088 running at 4.77 megahertz, the number of seconds that this program takes to run will be the number of cycles that the bank switching code takes. Now we have to adjust our estimate a little bit because we've added some extra instructions here. So I wanted the odd and even cases to be taken roughly half the time each. So I need AX to be odd every second run through. And to get it to be odd, I just increment it by 1. So this extra inc instruction takes another byte, and so that's an extra 4 cycles. Of course, it's only running every second run through the bank switching code, so that means we have to add an average of an additional 2 cycles to our original estimate. So I think we had an estimate of 43.5, so that goes up to 45.5. And there's also a little bit of overhead for the loop itself. You can't get rid of it completely. Obviously with a very long loop body like this, it goes down a lot, but it's still there. So I think there's 50 cycles per loop iteration, and if you average that out over 100 calls of the bank switching code, then it's about an extra half a cycle on average that we have to add to our estimate. So we're now looking at 46 cycles as our estimate for the first piece of bank switching code. So let's actually assemble this, and then we can actually see if we were right about the number of machine code bytes that our little section of bank switching code takes. We'll open it in the debugger and actually count the bytes of machine code. So let's just do debug bankswitch1.exe. I'll just unassemble it with the U command. You can see the first line there is just loading that 47,700 constant into my loop counter, CX. And the next line is just making AX odd for that first iteration. And then I start executing the bank switching code over and over. So first of all, you can see that the first instruction, shift right AX by 1, goes to the machine code D1E8, which you'll see to its left. And so D1E8, that's 4 digits, and there's 2 digits per byte. And that's the nice thing about hexadecimal. So in other words, we have 2 bytes here. The next line is SBB SISI, that's 1BF6 in machine code, and that's 2 bytes. And similarly, the next line is 4 bytes and then 2 bytes again. So those are the numbers that we guessed. So this is right. Finally, the INCAX down there, you can see that's 40 in hexadecimal, and that's just 1 byte. So that's great. So everything checks out here. So let's take a look at the second program, which I've imaginatively called Bankswitch2 Asm. So this was a little bit more difficult to code up because of the branches. Obviously all the labels need to be unique, and so it took a little bit longer. It's not just a simple cut and paste job, but I got there in the end. And naturally I should have done this using a macro, and I probably should be using timing code, but it's just fun to do it this way sometimes. And so this particular piece of code is almost exactly the same in every other respect, except that we now have the jump in there. So let's take a look at this one in the debugger as well. So I'll just assemble that one and link it, and then we'll be able to open that up and see whether the assembly language instructions that we have there are what we imagine. So let's take a look, debug Bankswitch2.exe, and I'll unassemble again. Starts off the same way, of course, and then you see the shift right AX by 1, still 2 bytes. Jump if no carry. Now that's actually the same assembly language instruction as jump if not below, and that's 2 bytes of machine code. Then we have the XOR DI 2000, so 2000 is 8192 in hexadecimal, and so you see on the left there 81F70020, so that's 4 bytes, and then we're done. So this is actually very, very short, this sequence of code, so we will expect this to go faster. So what's our estimate here? Well, I think we had an estimate of 32 cycles plus overheads, and we added 2.5 for overheads, so 34.5. And we have to add all these same additional overheads for the INCAX and the loop, which came out to 2.5 cycles. So I think we're going to have an estimate of 37 cycles here. Now bear in mind that was with my guess, total guess, that there would be 2 bus cycles wasted every second call because of the fact that the prefetch queue is loading that XOR DI instruction, or partially loading it when it doesn't need it. So we'll see how close that is. That's a total guess on my part. I have no idea how long it's going to take. But 37 is our guess, and we'll see how accurate we were with that. So I'm going to run this now on some real hardware, on an 8088 at 4.77 megahertz, and also on an 8086 machine, probably at 8 megahertz, and I'll also run it on a 286. I'm not exactly sure how fast it'll be. I think I'll use perhaps my 6 megahertz machine. At any rate, I'll figure out all the numbers and I'll come back momentarily, and we'll see once and for all which of these pieces of code is quicker. Well, let's analyze the 8088 timings first, and these are the times that I actually got. Now, I wouldn't read too much into these. These were done with a stopwatch by hand, and so my timing accuracy is probably like half a second or something. And also there's a little bit of uncertainty anyway, because DOS has to load the program from the disk, and there's also exiting to DOS and so on, and that takes a little bit of time. So these times are not particularly accurate. But at any rate, we guessed 46 seconds here, and that seems to be about right. It's very, very close, and that's not surprising given how easy this piece of code is to analyze. But this one here, it seems like I screwed that up. I guessed 37 seconds here, and so we have to go back and look at what I could have got wrong. And pretty much the only thing is the stall for when it's loading the wrong instruction, when the branch is actually taken, and it should be loading this one instead. So there was a stall that we added, and I guessed 2 bus cycles for that, or a total of 8 cycles. and we halved it because it only happens every second time. It only happens when the branch is actually taken. And so in the end we added 4 additional cycles for that. So obviously that was not correct and needs to be revised. So let's reanalyze. You remember that when we just took the bottlenecks of all of the prefetch and execution times, we just got 28 cycles. Then we have to add some overheads, and I was adding 8%, and so I guess that would bring us up to about 30.5 cycles or thereabouts. And then we had the additional time for our inc.ax and also for our loop overhead, and that was an additional 2.5 cycles. So I think that brings us to 33, which is really perilously close to this 34.5, actually much closer than I thought. So these stalls can't be very much. In fact, we only have 1.5 cycles left, and I double that because the stalls only happen half the time. So the stalls must be something like 3 cycles or thereabouts. Could even be less if the overheads are more than I was anticipating. So very surprising result actually, that these stalls really aren't that expensive after all. So now let's look at the 8086 timings. And here they are, and you can see that these times are much lower than we had on the 8088. Now this is an 8 MHz 8086, but I did 8 million iterations of each just so that we'd be comparing cycles with cycles. So this is really literally almost half of the cycles that we had on the 8088. Now the execution times of the instructions on the 2 CPUs are basically the same for almost all the instructions. So the real difference has to be the prefetch times. And in fact, the 8086 is a 16-bit data bus, so it can load 2 bytes from memory at once, or up to 2 bytes, in a single bus cycle. Now the bus cycles are still 4 CPU cycles, they're just doing twice as much work. And so there is one caveat, however, and that is that it can only do a 2-byte load in a bus cycle on aligned accesses. So what that means is that the memory address has to be an even address. Now that actually doesn't affect code like this because the prefetch queue just goes ahead and loads pairs of bytes and doesn't really care whether it's instructions or not. It just loads up as quick as it possibly can. And so you can really just take 2 cycles per byte for code like this. But this piece of code will actually cause a problem with alignment, and that's because of this jump. Imagine that this jump if no carry actually takes the branch. So the prefetch queue will have been sitting there loading this up. It will realize the branch is going to be taken, and it will then have to empty the prefetch queue and start again. And if this is an odd address, then it's not going to be able to do an aligned access. So that means that it has to do an additional bus cycle for that first byte that it has to prefetch, and then it can start doing 2 bytes per bus cycle. So this does mean that we've probably got a penalty here for our laziness, and in fact it's actually as bad as it can be, I think, because we have an inc.ax stuffed between every second one of these fragments, and so that's almost certainly going to make every second one of these an odd address. So we will probably incur some kind of penalty for the unaligned access every second run through. At any rate, I didn't really talk about how we would estimate the number of cycles here, but as you probably guessed by now, it's pretty much the same as the 8088. You just take the minimum of the prefetch time and the execution time. And here we have 10 bytes of machine code, which will take now 20 cycles to load, and that is the bottleneck. So now if we work this out, we're going to get 20 cycles for the prefetch. We have an inc.ax instruction in between every second one. That's 1 byte, which will take another 2 cycles on average to load. and it's only happening every second run through, so that's an extra 1 that we have to add. So we're now up to 21 cycles, and there's probably another half a cycle for loop overhead, so 21 and a half would be our estimate, and the rest just has to be overheads, things like memory refresh and so on. This one down here, we have some differences. So the first instruction is only 2 bytes, and so it now only takes 4 cycles to load, and so that means that we have 4 cycles as the bottleneck, because the execution time is not above that. So then this instruction, we also have 2 bytes, and so again 4 cycles for the bottleneck. The execution time is only 4 cycles when the branch is not taken. The other case where the branch is taken, we still have 16 cycles for the execution time. So on average we have the average of 4 and 16 now instead of 8 and 16. And so we're going to end up with 10 cycles on the 8086 instead of the 12 that we had on the 8088. So we've had a 2 cycle saving here. So far I think we have 4 plus 10 is 14. And here we have 4 bytes, which will now take 8 cycles to prefetch. But it only happens every second run through, because it's only happening when the branch is not taken. So that is an average of 4 cycles here. So we have 4 plus 4 plus 10 is 18 cycles. And then we add our 1.5 cycles, makes 19.5, and the rest has to pretty much be overheads. So you can see that the overheads on this particular 8086 machine are quite high, certainly not anywhere near the 8% that we had on the 8086. But anyway, that is basically how one can analyze the 8086 code. So now let's move on to the 286 machine. Well, we now have the 286 timings, and these you can see immediately are way lower than the 8086 ones even. In fact, they're basically twice as fast again, especially in this case. Interestingly enough, this piece of code is now slightly slower than this piece of code, which is a change. Now this was a 12 megahertz machine, so I've scaled everything up by a factor of 1.5 here, just so that we're comparing cycles with cycles again. Now to work out the cycles here, most of the short running instructions on the 286 are about a cycle faster than the other CPUs. This one's actually the same, so it's 2, 2, 3 and 2 here. So that gives us a total of 9 cycles execution. Now the actual loading time for this is dramatically better, and that's because the 286 has a 2 cycle bus cycle. So two processor cycles per bus cycle, and so that means it's twice as fast again than the 8086. In total, this 10 bytes of machine code will take just 10 cycles to load, and so 10 is bigger than 9, so that's the bottleneck, and that's almost all of the time. The rest is just some overheads. So the second piece of code is a bit more complicated. We have 2 cycles still. This instruction, however, takes 3 cycles if the jump is not taken, but 7 plus m cycles if the jump is taken, and m is the number of bytes in the next instruction, which I presume by that they mean this one here. That's 4 bytes, so we have a total of 11 cycles if the branch is taken. So the average of 3 and 11 is 7, and finally this line of code here is 4 bytes, which will take 4 cycles to load, and it will execute in 3, so 4 is the bottleneck, and it's only run half the time, so we have an average of 2 cycles here. So 2 plus 2 plus 7 is 11, which is again most of this time. So actually on the 286 it's not that hard to work out how long things take to run. Just add maybe 10% for your overheads or something like that on top of the bottlenecks that you get. And so it's really interesting that this code is now slower because of this really weird timing for this instruction here. So you might actually think about whether there's another way to do this with a shorter instruction following a jump, which is a crazy thing to think about, but that is how the 286 works. And I have no idea why that is. That's just a mystery at this point. The data sheet doesn't give any information on that, well, at least not where the table is. Maybe it's described elsewhere. So anyway, just to summarize, basically this piece of code here gets twice as fast as we go from 8088 to 8086, twice as fast again from 8086 to the 286. The first speed up was because we get 2 bytes per bus cycle, and the second speed up to the 286 is because the bus cycle itself is half the length. This piece of code doesn't fare so well. In the end, it's slower on the 286. On the other hand, we're writing for the 8086 and 8088 in this series of videos, so we should clearly be using this code in our lead-in. So thanks to Jim Leonard for suggesting this. Rather long video to explain all that, but I think this is really interesting stuff, which is very useful when you're writing assembly language on these machines.